Good evening. Good evening. Audio is clear. Audio is clear, madam.
Yes, sir. Yes, sir.
Yeah, we'll start. Good evening on this wonderful day. Even though we have a lot of problems across the country, we are able to somehow make it. The most unfortunate thing is the most unfortunate thing is because of the situation in Karnataka, the corona situation, due to difficulties in transportation. Mr. Pai, who is the presenter, he is not able to present today, and he has a lot of Wi-Fi network issues at his home, and we tried a lot, but we could not get through. And Mr. Pai has requested me to present on his behalf. I'm Kaushika, Director of QCrete Readymix Concrete Private Limited, and under these circumstances, I have to present on behalf of Mr. B.V. Pai. You know, the situation throughout the country is not good because of the corona, and I am thankful to all of you who have come to hear from B.V. Pai, but due to some extraordinary circumstances, he has requested me to present, as there are a lot of problems with his connection, and he could not be brought to a place where he can present. Actually, due to a lot of restrictions in the movement of people in Bangalore. So we'll start today about this wonderful subject, ultra high performance concrete. To be precise and honest, actually, not much work has been done about this kind of concrete in India. Mr. B.V. Pai himself has done a lot of work on this, and it is his interest area. And we'll go through the basics and fundamentals of ultra high performance concrete. And it is sometimes, I feel it is very extraordinary thing that instead of not even at a level where we can speak of high quality normal concrete in India execution. Okay, we have a lot of theories, we have a lot of concretes done, normal concretes M20 to say M50 normal concretes are done, but even there we have a lot of failures, a lot of problems due to various issues introduced not only during production but much later. A lot of problems are introduced much later. So in the situation that we are in, still in India, it is early, I can say, to talk more about ultra high performance concrete. But nevertheless, as we are moving forward with concretes like specialty concretes like SCC and all, it is our duty to refresh and be aware of what are the developments that are happening across the globe, especially in the field of ultra high performance concrete. So in this attempt, we are trying to talk something on this field. Ultra high performance concrete is generally a concrete which is high in strength, 120 to 150. It is limited to concrete that has a minimum specified strength of about 150 MPa with specified durability, tensile ductility and toughness requirements. So high performance concrete, we know what is high performance concrete. High performance concrete where the performance of concrete is defined by its permeability, by its shrinkage characteristics, by its chloride resistance, by its sulfate resistance. Overall, the performance criteria are introduced. This ultra high performance is the next level where very high strengths are gained in concrete. Also, very high performances are expected of the concrete. UHPC typically exhibits elastic plastic or strain hardening characteristics under uniaxial tension and has a very low permeability and discontinuous pore structure. This is one of the, you can say, important characterization of ultra high performance concrete. It has almost negligible permeability. Ultra high performance concrete consists of cement, silica fume, fine quartz sand, high range water reducing admixtures, and fibers with water bender ratios probably between 0.15 to 0.25. And many times, a lot of variations in UHPC matrices have been developed that contain other supplementary cementitious materials and sometimes coarse aggregate. Normally, whenever we are talk of ultra high performance concrete, generally very fine materials are introduced in the body of concrete to make such kind of concrete. However, sometimes 8 mm down aggregates with quartz sand or silica sand is introduced to make such concretes. But as in general, ultra high performance concrete consists of Portland cement or cement, silica fume, and very fine particles of sand. So this is a picturization of the components of UHPC material. You have, as it talks about sand, it talks about cement, silica fume, water, superplasticizer, basic. These are the basic components. Added to that one, you have steel fibers, which is very, very important in increasing the ductility, toughness, and tensile strength. And here we can say silica fume plays a major role in bringing the higher and higher strength and higher performance into the concrete matrix. And we have seldom seen any much literature on ultra high performance concrete without silica fume. Most of the literature, most of the work across the globe where ultra high performance concrete is done mostly on silica fume, and very rarely we see some products like metakaolin or something like that, or in combination of silica fume, some metals replacing to some extent actually. So basically, these are the components of ultra high performance concrete. So the most important characteristics of ultra high performance concrete is its homogeneity, and this homogeneity is enhanced by eliminating coarse aggregates. So we talked about coarse aggregates. So if you have a lot of coarse aggregates of different sizes, like in the case of normal concrete, the homogeneity may be lost. Homogeneity will not be that much. That is the reason the shift is towards finer particles, which can be packed well and which will give enhanced performance. Density enhancement by optimization of the packing density of the matrix. This is achieved through optimizing gradation and mixture proportions between the main matrix constituents. Ductility enhancement is done by introduction of fibers. As the matrix is very brittle, fiber reinforcement is added to obtain elastoplasty or strain hardening behavior in tension. Typically, UHPC has fiber contents of about 2% or more by volume. The maximum fiber content is a function of the fiber aspect ratio and fiber shape, as well as production issues such as workability. So addition of fibers, basically steel fibers, brings the other dimension in the case of UHPC as far as the ductility is concerned actually. So ductility enhancement is achieved by introduction of the fibers. The fibers are basically steel fibers, and there are cases where we find combinations of steel fibers and other fibers. We will talk about that one. UHPC, how it has evolved, how it has developed, and we are going to go have a very brief review of these things actually. Now, first we will talk about something on modern concrete. The modern concretes are initially, as a part of history, once Joseph Asparin introduced this wonderful material called cement. After that, normal concretes came into existence, and we have been using normal concretes for now almost a long time, maybe a century. And then now, after that, we started using concretes with superplasticizers, that is free flow concrete, high flow concretes, self-compacting concretes. Such concretes came into existence which are being used, and then now as a final stage, kind of a final stage in this kind of evolution, we have moved towards ultra high performance concretes. And in ultra high performance concrete itself, a lot of innovations have been made by different researchers, and different applications of these materials also have been found. Now, we can see from this graph, over a period of time, in the last 100 years, concretes started with a low strength actually. You can see the concretes in 1900s used to be around 20 below that one, and then slowly the strengths have gone up actually due to evolution and research and improvement in materials, inventions such as superplasticizers, hyperplasticizers, supplementary cementitious metals, etc. The strengths have shot up to 200 or more than 200 we can produce, but the common applications are here in this represented by this blue line. The common applications now, for example, if we talk about India, I can say clearly 70 to 80% falls under 2025 or maximum M30, including the even if we are doing self-compacting concrete and such concretes, the strengths are not very high, and you can see all over the world the utilization or harnessing of the strengths actually available are in this level, but applications are in this level. So as I said in my introductory remark, that we are in infancy as far as the utilization of ultra high performance concrete is concerned, at least as far as the geographical boundaries of our country. Now, the major characteristics we have already discussed about ultra high performance concrete. In this, composite strength is also one of the major characteristics. And if you are talking about compressive strength versus water binder ratio, so to get higher strengths than 100 MPa, you need to shift the water cement ratio towards 0.2 to 0.21. Then only you will get a compressive strength of 100 and above. And we can see through these graphs, we can see through these graphs actually with the different combinations of materials. By keeping a water cement ratio closer and lesser than 0.24, you can achieve higher strengths, higher than the normal concretes. And if you want to shift towards 100 and above, you need to go towards water binder ratio of 0.21. Now, the major difference is the packing. Actually, you have in conventional concretes materials ranging from 20 mm, 12 mm, different sizes of sand, and then cement, things like that. Whereas in ultra high performance concrete, you have cement, microsilica or silica cube, and then packed well between finer particles, and the size of the inert fillers, for example, sand is very low. It can be between 0.1 to some nanometers. The first commercial applications of UHPC started in 1990s in Europe and has spread worldwide. Several major research programs on UHPC have been carried out worldwide. Japanese Society of Civil Engineers, a large federally funded program in Germany, as well as several research programs in Canada and United States. UHPC has been used in multiple applications as small bridges, infrastructure, facades buildings, elements in aggressive environment, and for security and blast resistance. Applications include new construction and rehabilitation using both cast-in place and precast UHPC components. UHPC in its present form became commercially available in North America approximately in 2000. UHPC is still in process of finding a broader use. The objective of this report is to introduce UHPC through a brief overview of production, properties, design, and applications, and to promote further use of UHPC and integration into today's construction market. Because the cost of UHPC is high when compared to conventional concrete, use should be focused towards applications that engage several of the exceptional properties of the material. Current research needs have been identified as improved design guidance, standardization, and broader material knowledge. So, for example, the most important aspect here is cost actually, especially as far as the Indian concrete market is concerned, very highly price sensitive market where people bargain, talk a lot for paying M25 concrete, money for M25 concrete. And if you're talking about a UHPC concrete, which can last for 100 years or 150 years or 200 years. So many people do not appreciate the life cycle costs of the concrete and what is the low maintenance costs it can bring in. So many times cost becomes the initial application cost becomes vital, and hence many of the projects which UHPC does not take off. But having said that one, researchers, concrete technologies throughout the world are making efforts to reduce the cost of UHPC and bring it down to the level of where it will become attractive to common man. It may not happen immediately, but UHPC will gain ground slowly and steadily over the next 5 to 10 years, and people really start appreciating in future, and cost will incidentally eventually it will become secondary. The materials used to make ultra high performance concrete are similar to those commonly used found in traditional concrete, and UHPC materials are selected based on their particle size to optimally pack the matrix to reduce voids between the particles. While some commercially available UHPC mixtures are proprietary, with their exact composition not reported, other mixture compositions are readily available. Some mixtures feature less common components such as silica floor, which is silica sand ground to achieve a specific particle size. The addition of high-strength steel fibers to the matrix results in improved ductility and the ability to eliminate some of the mild steel reinforcement normally found in conventional reinforced concrete members. Here, generally, how the UHPC can be done, a lot of work has been done, it is available, and we can take this as a start off point actually, but our interest and intelligence should be to use the locally available raw materials. And there are a lot of companies abroad working in Germany, US, etc., who are probably achieved very great things in terms of extraordinarily characterized UHPC mixtures which are proprietary, means they don't tell what they have done to achieve such mixes. It is proprietary, but general mixes as a starting point to a concrete technologist or a researchers is easily available. The high strength and superior performance achieved with UHPC stem from reduction of void space in the matrix and discontinuous pore structure, depending more on the material's behavior on a microscopic level than on the properties of its constituent components. Through the proper selection of components based on both their particle size and mechanical properties, the number of contact points between particles is increased, which is in turn causes the level of stress transferred between particles through the paste to be reduced. So mixture proportioning of UHPC is not like conventional mix design or mix proportioning. You can say this is the next level of science where the particle packing and packing density is given importance, and there are a lot of softwares algorithms developed by some companies which are, you can say, proprietary or secretive in nature to achieve ultra high performance characteristics with the locally available materials. So this is from ACI, where they have given two possible UHPC mixture proportions, and you can see here huge amount of silica fume, which is, I can say, as we discussed earlier, it has become the silica fume is part and parcel of these kind of mixtures. And you have sand, quartz powder, high range water reducing admixture, water and steel fibers. So these two have been given, and these can be used as a start off points for making ultra high performance mixtures using the locally available materials. In fact, UHPC is a new form of concrete with a new type of composite construction material. Its high compressive strength and ductility are achieved by an optimized packing of fine and ultra-fine particles as well as the inclusion of steel fibers. This optimization in particular will evenly distribute all particles at the micro scale to pack the spaces surrounded by larger particles. Accordingly, a dense matrix is achieved with low permeability to provide a concrete with superior properties. So you can see in this table also, huge amount of cement per cubic meter has been used, and good amount of microsilica with again significant amount of steel fibers, and mm, uh, the this is 40 kgs of superplast is almost unheard of in normal concrete, and it is almost, you can say, unthinkable for people who have worked for a long time in conventional concrete to think of such dosages which you can see here. So these numbers are just guidelines given based on the um, some concrete technologies, his experience or some research scientist's experience somewhere. The same dosage may not be used or cannot be used probably in other circumstances with other materials elsewhere in other countries. Different definitions have been given to UHPC. Some researchers define the term based on its major components. For example, Farzad defines UHPC as cement-based material formed with an enhanced degradation of granular components, a water to cementitious materials ratio of less than 0.2, and a significant portion of internal fibers. Mishran Singh defined UHPC as a special type of concrete that consists of highly fine-grained reactive admixtures, silica fume and fine quartz, fibers, and superplasticizer, while having more binder content and low water binder ratio. Azmin Shafiq defined the term as fiber reinforced superplasticizer silica fume cement mixture with a very low water to cement ratio, characterized by the presence of very fine quartz sand that ranges from 0.15 to 0.6 mm in diameter instead of ordinary aggregate. So the definitions are different as given by different people here, and we need to know that at this moment it is completely different when compared to conventional concrete, and achieving the required properties with different locally available materials will require a lot of detailed study of material characteristics, particle packing, and detailed study of all the sources of different materials and their properties. Ahmad again defines UHPC as a mixture produced by using high contents of cement content silica fume 0.1 to 1 micrometer and superplasticizer along with very fine quartz sand, quartz powder, and fibers without coarse aggregate. So you can see different people defining in their own way actually. For example, Aurora defines UHPC as a multi-scale microstructure designed material tailored for very high strength, compressive strength, high flexural and tensile strength, high ductility. Defines the term as an innovative composite material that can serve as a potential candidate for concrete structures exposing to aggressive environment. This is the most important point actually. The resistance to chemicals, resistance to aggressive environment is enhanced significantly when we are talking about UHPC. The durability also is improved in the proportionately. The matrix of UHPC is optimized for particles packing, that is, the mixture proportions of typical components such as sand, silica fume, and cement are optimized to achieve the densest packing possible, as investigated by Dillard and Cedron. Another unique aspect of UHPC is that some cementitious metal particles may not take part in the hydration process, but merely serve as fine aggregate in the overall matrix. It is common for 30 to 50% of the cement to be hydrated in UHPC due to the lower water content. So, due to the lower amount of water content available, as we are using very low water cement ratio, some of the cementitious products may remain as unsaturated or unreacted in the body of concrete, and they can remain forever in that state. We could come up with a definition which combines UHPC major component and superior properties along with the basic technologies behind the UHPC production. Thus, UHPC is a new generation of cement-based construction material tailored for very high compressive strength, high ductility, sustainability based on micro-scale optimization of fine and ultra-fine aggregates, lower content of water to cement ratio with added superply scissor and reinforcement with high strength steel fibers. So you can see here one of the particle size distribution requirements made by one of the scientists actually, and silica sand is expensive for UHPC. Quartz sand, on the other hand, is available, but it takes to be crushed from coarse aggregates on natural sand. Natural sand, in contrast, can be used easily and effectively as a fine aggregate for UHPC. And in Saudi Arabia, they have used dune sand, which is easily available. And this also shows some research where relationship between compressive strength and silica fume content. As the silica fume content goes up to 15% here, then the compressive strength breaches the mark of 110, 120, which is required for UHPC. That is why silica fume has almost become an integral part of UHPC. Portland cement. Ordinary Portland cement is primary bending material. When used with water, hydrates and becomes solid and binds all aggregates of the UHPC concrete. It is produced mainly from two basic raw materials. We know all these things actually, which are basic, and the content that is used in ordinary concrete cannot be compared with this one. Almost you have double the cement content in the UHPC. The part of the cement that is not hydrated due to the small proportion of water will be used with other aggregates for packing optimization. So it is very, you can say, from a common man's point of view, cement being used as a packing material is unheard of, but in UHPC, if a lot of material is unhydrated, it will be working as an inert filler and it will be filling up the spaces between the larger particles, and it will be responsible and it participates in packing optimization. We have spoken a lot about silica fume so far. Silica fume or microsilica is a waste byproduct material coming from furnace smoke of the production of silicon metal and ferrosilicon alloys. The rounded particles of silica fume have a diameter of 0.15 mm on average, and most of the particles are lesser than 1 mm. Thus, they are smallest particles in UHPC matrix, 100 times smaller than cement particles. This is why it is considered an excellent filler to fill the voids between larger particles in the UHPC matrix. Using this ultrafine material leads to a dense matrix which enhances the mechanical and durability properties of the concrete. So microsilica, because of its shape and size, it acts as a filler. Also, it reacts with the other hydration products making durable and high strength and extraordinary concrete as the amount of microsilica goes up in the matrix. So silica fume can be used in UHPC mixtures within a range of 150 to 250 kg, which is huge in compared to a conventional concrete. In conventional concrete, we are all aware microsilica is used between 5 to maximum 6 or 7% normally. So here it is used between 10 to 30%. And we have seen the relationship between the compressive strength and silica fume content in UHPC concrete. As shown in the figure, concrete strength of 81 MPa can be obtained without microsilica. However, by increasing the content of silica fume, the compressive strength is rapidly increased. One of the main disadvantages of this material that it requires more water because of its extremely fine particles, but with superplasticity, the same water content can be maintained. So microsilica, as we know, is a water-hungry product. It kills the slump. We can say it kills the slump. It reduces slump from the general slump that we get without microsilica. But the advantages are plenty. Even though you can make concrete without microsilica and get some high strength, many times in our experience, we can say microsilica is like an insurance. Whatever happens, if some mistakes happens during production or during transportation, microsilica will take care of that one and it will give as a additional strength, as a strength boosting material as the age goes on, and 28 days and beyond also it will improve the strength, and it is a material accepted worldwide for use in high strength concrete and also ultra high performance concrete. So even though it requires more water or more admixture, it is a product which is used worldwide wherever high strength, high chemical resistance, low RCPT values are required. Water is an essential material for making UHPC. Potable water is suitable as is usually used for ordinary concrete. The quantity of water must be enough to complete the hydration process and to maintain workability. The minimum water to cement ratio for ordinary concrete is about 0.4 to 0.5, including water for workability. The amount of water is inversely proportional to the compressive strength. If water increases, the strength decreases. Excess water not used in hydration would develop voids in the concrete mixture, which would increase permeability and reduce the strength of concrete. In UHPC technology, using a high-range water-reducing admixture helps to maintain workability without the need for excess water. Accordingly, the water-cement ratio will be reduced to an optimum level ranging from 0.4 to 0.14 to 0.22. This leads to increased compressive strength. So 0.14, 0.22 are earlier unheard of water-cement ratio. Unheard of water-cement ratios, but in UHPCs we use 0.14 to 0.22. We have UHPC. We have UHPC. In UHPC, you use high range water reducing admixture. Now, polycarboxylic ether based admixtures are available. Extremely advanced admixtures are available, which can be used in very high dosages without affecting the setting time of concrete. So if you use, even if you use at very high dosages, these admixtures are tailor-made to such an extent, in such a way that they don't disturb the hydration process or setting time, and hence they are part and parcel of ultra high performance concrete. The reduction of water cement ratio to 0.14 or 0.22 is possible only because of such extraordinary water reducing capabilities of polycarboxylate ether based materials or polycarboxylates. Concrete without reinforcement is liable to fracture since it is brittle in nature and cracks cannot be stopped. Therefore, steel fibers are used to reinforce UHPC matrix to provide a better resistance towards crack generation and a better tensile strength and resistance to fracture. Steel fibers are characterized by their shape, diameter, volume, orientation, and strength. The mechanical properties of steel fibers are also there. Deformed fibers such as hooked end fibers are much better than straight ones. Also, long fibers are better than short ones. With respect to the fiber's volume, an increase will improve ductility up to certain limit, beyond which additional content will not be beneficial. Content 1 to 2% of the expensive fibers has been proved to be enough to achieve the required properties at a wise economy. Also, fibers with a good orientation along the direction of the tensile load lead to good homogeneous distribution of fibers, which will improve the mechanical properties of concrete. So, as far as the dosage is concerned, 1 to 2% of steel fibers has to be used. Tensile behavior of UHPC, idealized simplified response to strain hardening, and here you can see supplementary cementitious material. What is the role? We know when you are using fly ash, workability, heat of hydration, setting time is increased, heat of hydration is reduced, setting time is increased, GGB is also workability is increased, silica fume it is decreased, hardened property strength increased when you are using all these materials, permeability is reduced, and when you are using silica fume, maximum reduction takes place. Chloride ion resistance and sulfate ion resistance is enhanced significantly, and if you look at the particle size, silica fume is the smallest particle, and you can see here whenever we are using supplementary cementitious materials, and since supplementary cementitious materials are part and parcel of ultra high performance concrete, the overall durability, that means the characteristics such as permeability as measured by DIN 1048, chloride ion resistance as measured by ASTM 1202, resistance to sulfates, drain shrinkage, abrasion resistance, freeze thaw resistance, long-term durability, long-term strengths, all are improved by introduction of these materials along with a containment of water cement ratio to less than 0.21 or lesser than around 0.21 and below 0.21. So is UHPC has already been used somewhere? Yes, there are a lot of examples. A footbridge in Korea. This is first ultra high performance concrete highway bridge in USA. 120 approximately 120 MPa strength. Again, a stylized light rail transit system set to be in US again. Very innovative canopy has been made by using this ultra high performance concrete. And you have a lot of other applications can be done by using ultra high performance concretes. You can reduce the thickness of structures. You can reduce the column thickness. You can reduce the steel. you can really take the construction, reinforcement construction to the next level by using UHPC. Hybrid beams, some people have attempted hybrid beams with bottom layer of UHPC and then again on the top high strength concrete, and somebody has attempted UHPC bars which can be embedded in concrete. Hybrid specimens reinforced with 2 UHPC bars. Hybrid hollow core specimens before casting ordinary concrete. You can see it is already cast, and then on top of it one they will cast the normal concrete. UHPC has been a major development in concrete technology in the first 20 years of 21st century. A bridge deck, you can see, for using UHPC as a repair material. People have investigated concrete UHPC as a repair material. The interfacial bond and the permeability characteristics were evaluated. The results showed that the behavior of composite was firm and stable due to the UHPC overlay. So bridge decks, repairing of old bridge decks have been done. The study revealed that UHPC was efficient and stable for concrete repair. Also, Roy used an effective mixture of UHPC as a repair material for normal concrete. The study was conducted to investigate the bond strength between UHPC and substrate of normal concrete. The study revealed that UHPC was effective for repairing deteriorated structures. Another utilization of UHPC in hybrid structure is in timber concrete composites. The two materials are bonded together either with mechanical fasteners or rigid connections. Their advantages are utilized in one composite to achieve better performance. Detailed reviews of this timber composite concrete, including its connection systems, were carried out. Combining UHPC with wooden structures was also investigated by Ferrier. A hybrid beam was made of glued, laminated wood and UHPC planks. The investigation showed that the use of UHPC was optimized with better performance and efficiency based on greater bending stiffness and significant increase in structure capacity. With UHPC, it is possible to reduce the depth and to increase span of the beam without affecting the structure's performance. Some people also studied the possibilities of using UHPC in timber concrete composite floor structures. They designed a composite consisting of a timber beam and thin lower weight UHPC deck. Since it is difficult to use mechanical joints, they proved that gluing is good method to connect the two different materials. The study showed that the new type of composite would enable the design of UHPC deck with a relatively small thickness. And Holly and Fabric summarized the research findings on fabrication of timber concrete composite structures and suitable methods of coupling between two materials. They have presented ways to develop pedestrian and cyclist footbridges using innovative hybrids with efficient materials and better construction methods. Steel UHPC composite bridges also have been tried. It is current field of application for UHPC, which attracts many researchers to investigate the composite structure. Orthotropic steel deck steel plate covered by a roadway surface is used widely in many types of bridges, especially in long span steel bridge, earlier already shown. Despite having the advantages of lightweight and high load capacity, this type of structure suffers from cracks due to the fatigue problem under the load. Fatigue cracks are observed in many orthotropic steel deck bridges around the world, such as Severn Bridge in England, Sennetal Bridge in Germany, Westgate Bridge in Australia, the Bridge of Leverkusen in Germany. The fatigue problem has been studied by many researchers to improve the performance. One of the best prospective solution to restrict this fatigue is to use UHPC overlay as a deck payment instead of original payment. Fatigue response of using UHPC overlay with orthotropic steel deck was studied by Zhu. The study showed that UHPC overlay can significantly reduce the magnitude of stress at the deck side. Also, the transversal bending behavior under the bending moments of the steel UHPC composite deck was studied by Liu. The study found that the UHPC overlay has a considerable effect on ultimate load capacity of the deck. Going forward, there are specific companies, especially some companies in Germany, where they have made proprietary ultra high performance concrete, where you can see here the product is called as Cons Q156 with a compressive strength of 7 days 156, and you can see water cement ratio 0.292, slump is 29 centimeter, and porosity, permeability is not measurable. Concrete is pumpable. You have to mix for 5, and then it can be used for precast elements. The next is astonishing. It is 305 MPa, compressive strength 28 days. Flexural strength. You can see all these flexural strengths are significantly improved. The flexural strengths are very high when compared to normal concrete. You can see here the flexural strength is 45 MPa. Water cement ratio is 0.23. Porosity not measurable, permeability not measurable. Okay, mixing time is 5 to 6. So some companies abroad, like this company, has taken the ultra high performance concrete to next level, where they are talking about a strength of 305 MPa, 300 MPa. And you can see here the this product, ultra high performance concrete, where they are talking about 28 day strength of 80 to 300, 56 is 100 to 300, flexural strength is around 25, density has moved up. Most importantly, permeability not measurable, water absorption coefficient not measurable. So this is a totally different shift in the material performance. Ultra high performance itself, the technology is taken to next level by some patented technologies. Another example where normal curing, the strength is 128, 153. So here we should not compare with the strengths that we get by cubes. It is cylindrical strengths actually. So if you convert this to cube strength, it is higher actually. So you can see the capillary pores are less, shrinkage is less, and then creep is less, carbonation normal, sulfate resistance no damages. So fire resistance also is given, means the product has been defined and designed for even high fire resistance. So developed with local raw materials, perfect workability, earth moist to self-compact, means low to high, very high slumps are available, customized compressive strength, customized flexural strength, cost effective, sustainable, worldwide available. So here the high performance concrete, what they're talking about is 250 to 500 is possible, 500 MPa, and you can see here the range, normal range, and then they can go up to this kind of strengths actually, tensile strengths, flexural strengths, possible unit, you can make highly durable tile-like structures. Carbonation is less. Fluoride ion diffusion not measurable. Water resistance not measurable because it is an extraordinary material, different material, and the normal available standards cannot give the values for such a advanced material. Fire resistance, so we can see some of the structures done. It is a facade where 120 MPa concrete is done, and this is a material for facade. A bridge has been constructed in Germany by using UHPC 150 MPa concrete. 150 MPa concrete, and you can see the steps in a house. It looks beautifully done, aesthetically pleasing architectural design using ultra high performance concrete. Fire resistance is also significant. Fire resistance is achieved, okay, where 1350 degrees centigrade temperature load is withstood by concrete with a strength of 190 MPa. So conclusion that the new generation concrete has an amazing level of qualities that had never been thought possible before, and we can really harness the potential of this material for building high-rise structures, not only high-rise structures, but for many other normal structures also, where we can reduce the thickness, increase the aestheticity, increase the architectural look, and can be used for in myriad ways. The mechanical properties of the new generation of concrete are greatly superior to the properties of conventional concrete. These incomparable values are a function of water to binder ratio, ultrafine powders, optimized packing of particles, method of curing, and microstructural reinforcement. With this technology, it is possible to construct structures beyond usual designs, which are lighter, larger, with longer span. Its special workability enables the fresh concrete to be cast in irregular or very slender shapes to form structures with aesthetic appearance or extraordinary finish. However, the use of UHPC in construction is limited since it is not commercially available, but researchers are working around the globe to reduce the cost, and days are not far off when it will become easily acceptable as far as the costing is concerned. One of the suggested ideas to promote UHPC in construction is to explore alternative materials to replace the expensive composites of UHPC. Waste materials with cementitious properties were recommended to replace Portland cement and silica fume with the following advantages: reduce concrete production costs, make concrete more friendly to the environment, improve the homogeneity and density of the concrete for better strength and durability. So references are given here. I thank all the audience at the end of the session to have come, leaving their valuable work to attend to Mr. BBB Pai's lecture. As I said in the beginning of the lecture, Mr. BBB Pai could not deliver his lecture today due to various reasons, especially because of the Wi-Fi and other things in his where he stays actually. And it is remarkable that a lot of people have attended this on this evening, and we from the management of QCrete On behalf of our Managing Director, Mr. Shelly Fernandez, also we thank you all for attending this webinar, encouraging us, hearing to us amidst the corona crisis which the country is going through. And I am hope we will overcome the crisis which we are in. Any questions? You can either raise now or you can send the questions to technical@qcreteindia.com or myself. We thank once again your valuable time. Thank you very much. Thank you.